So a comprehensive approach to controlling and minimising squats in the rail network. The Sydney rail network is around 1,500 kilometres in length. We have around 1,900 turnouts and special track features, which makes it an extremely complicated system, running both passenger and freight every day. Axle loads up to 25 tonnes and over 1 million customer journeys per day. Okay. Across New South Wales, squats first occurred. Sorry. I don't know where it is. Is that better? Yep. Squats first occurred in the early 1990s, and Sydney trains started to run into squats in the early 2000s. And today, over 6% of our network is affected by this issue. We find that squats form under much lower tonnage than RCF, as has been said. And one of the other major things is squats, we read, don't occur in tunnels. So, for one of the interesting backgrounds that we found was after Hatfield, Sydney Trains rapidly increased rates of grinding across the network. And today we grind over 1,000 kilometres of our network every year. At the same time, we had a major issue with vertical split head rails across our system. And between 2000 and 2005, we had to re-rail the majority of our network. And we introduced head-hardened rail right through the system. And at the same time, we also introduced concrete sleepers and continued to push that program through. So we rapidly stiffened our track structure. We also rapidly increased our grinding frequency in an aggressive way. So a graph of how we've gone today, we're running at around 1,000 kilometres per annum of grinding. So aggressive grinding, trying to keep mainly the RCF issues under control. For a long period of time, we were re-railing over 200 kilometres of track per annum. So we've almost re-railed the entire system twice in the last 15 years and brought the concrete sleeper program in to, as I said, bring in a much stiffer track structure throughout the network. We analysed our squat reports from 2002 through to 2015 and looked at over 7,000 locations that we had issues across the network from squats. There's a lot of discussion about squats occurring at places of wheel slip, end of platforms, signals, those sort of areas. What we found were there were some hotspots, but squats occur all over the network. Throughout the system, we've got the problem, and there is no straight correlation with either geometry or with operational issues. Again, we've had no issue of squats occurring in dry areas of tunnels. As we said, head-hardened rails have been brought through the system. Variable grinding quality in our network with hard to get possession windows. The argument between quality and quantity is a big question. Generally, quantity wins. Keep the RCF under control has always been the rule. We've brought in Super Series traction and AC traction across the system. Concrete sleepers have stiffened it, and the wheel profiles have also led to tighter contact bands. White etching layer we see as the initiator, and we've found three major ways we can produce white etching layer out on track, either through severe deformation under severe shear, Facet corners on head hardened rail are a very good way of getting deformation to start to grow in our rail system. Intermediate temperature heating and cooling, which is the platform signals issues. We have produced the martensite issues down as far as 550 degrees centigrade under wheel pressure of 2 gigapascals. And finally, electric current leakage between wheel and rail is another way of producing the martensite white etching layer issues as well. So with the traction return systems, we're seeing those white etching layers produced as well. Squats originate in the brittle white etching layer cracking. High hardness, 700 to 1200 figures. We've produced that from what we've pulled out of track and checked. Either forming from transverse fractures of the white etching layer or from the edge of the white etching layer island itself. So, and forming an initial vertical crack. Again, squats are squat growth over a period of time. They can join up and cause surface material to detach and then create the spalling issues. We saw pictures of it earlier this morning, and it's been a major issue across our network. And as they spall, further damage then gets created through the impact loading. There is literature suggesting complete rail fracture and growing of these squats into a vertical fracture. We haven't had that issue directly from a squat, but we've run into squats that have then run into other issues and turned down as a result. So we've had pieces of martensite separately in our rail that have caused fractures to occur as a result. Hydraulic entrapment of water is critical for growing a squat. So we've taken out a piece of rail in a tunnel where a squat occurred under an air conditioning duct. Really big example. It was very clear in that section. Water was growing the squat quite happily. So in this situation, white etching layer does occur in the tunnels. Crack initiation forms. However, where you don't have the water, you just maintain an initial crack of about 0.5 millimetre deep. And we've found plenty of examples of that, living in tunnels that are just waiting to be watered and to grow. So one of the issues, or the good things we found, is curves under 600 metres don't produce squats as a rule. And we believe that the track curvature is critical, and that the rate of wear across the tighter curves reduces the opportunity for squats to occur, because we're wearing the white etching layer off at a faster rate than we can grow it. On flatter curves and tangents, white etching layer is happily growing and giving the opportunity to then crack and form the squats. One of the questions we've then asked is, in our system, how come? What's the rule of thumb that we need to start to adopt for preventing the white etching layer cracking? And so we've started looking at the fatigue curve of what the martensite layer is looking like. We don't see the squats appearing in the heavy haul system, and we believe that's about the axle load and the number of cycles that the white etching layer is actually seeing between grinding opportunities. So our approach moving forward to address squats is to bring in a grinding strategy across our network of around 11 million gross tonnes. Just a polishing pass that enables us to reset the rail at regular intervals. We continue to run the heavy grinding at the normal cycles, either 11 up to 30 million tonnes, depending on the geometry. But we're also introducing the polishing pass, very, very thin grinding, which then resets the rail at regular intervals. So, as we've improved our track, we've developed a stiffer track structure. We've suffered squats right across our network. We've been able to demonstrate developing squats 3 different ways, which helps us to understand why there's no particular one situation or one location that causes them. Brittle white etching layers lead to the initiation of squats. Water's not essential. You'll still get the cracking occur. However, the water promotes the crack growth by tensile opening due to pressurisation and entrapment. And there's other research we've done on this that shows how it grows. And at the end of the day, we're now implementing a different grinding strategy to start to address this issue and keep it under control. So, again, I'd like to thank Hongtao and his team from University of Wollongong who've helped to make this a successful paper. So thank you.
Thank you very much. And yes, question? Yes, Robert, please. Yep. Over there.
Next question.
Thank you for a nice presentation. My name is Michael Steenbergen. I would like to ask you, could you say something about the effect of the rail grade? Because that was not mentioned. I was wondering a couple of times, what rail grade are we talking about?
Sorry, I didn't quite catch the question.
Could you say something about the rail grade? So the effect of the rail grade in your, on the examples that you have shown us. So which rail grade are we talking about? Is it the premium grade, conventional grade, standard grade? The
cracking of the rails?
Yes.
Yeah, the cracking of the rails were predominantly head-hardened rail, 380 Brunel rail. They've come out of track as samples of rail from in-track conditions.
So basically we are talking about head-hardened rail here?
Yeah, but we're also seeing it in standard carbon as well.
Okay.
Yeah.
Thanks. That's clear.
Yeah.
Yeah. My question is, when you install new rails, do you initial grind them?
Yes. Yeah, we take off the decarb zone.
Okay.
Yeah.
How many passes?
However many it takes to get it to profile.
Okay.
Hopefully less than 5, but it depends on the situation.
Yeah.
And depends on the number of stones available as well. So we run a 60 stone grinder, and an initial grinding pass is probably 3 to 5 passes.
Hi, I'm Andy Wexler from London Underground. I think a lot of the initial work was the same, and I don't really have a question. I was just going to say everything you've said we would fundamentally agree with, only ever really in open sections, and we find grinding to remove the white etching layer, we get about 2 years, which would be about 30 to 40 million gross tonnes of no squats.
Okay.
So someone else out there does the same thing.
Okay, very good.